Vibration Analyst, peak, peak-to-peak, RMS, and Crest Factors Understanding key vibration measurement techniques and parameters. Importance of vibration parameters. Vibration analysis is a critical aspect of predictive maintenance and machinery health monitoring. Understanding parameters such as peak, peak-to-peak, RMS, and crest factor is essential for diagnosing mechanical issues like imbalance, misalignment, and bearing defects. These metrics provide insights into the amplitude and energy of vibration signals, helping analysts determine whether a machine is operating within safe limits or exhibiting signs of failure. By interpreting these values correctly, engineers can prevent costly downtime, improve reliability, and extend equipment life. Each parameter serves a unique purpose. Peak indicates maximum instantaneous amplitude, RMS reflects overall energy, peak-to-peak shows total excursion, and crest factor reveals waveform shape characteristics. Together, they form the foundation for accurate vibration diagnostics. Basic definitions: understanding waveform terminology. Waveform terminology is fundamental in vibration analysis. A vibration signal is typically represented as a time-domain waveform showing displacement, velocity, or acceleration over time. Key terms include peak, which is the highest positive amplitude, peak-to-peak, the difference between maximum positive and negative amplitudes, RMS, root mean square, which measures the effective value of the waveform, and crest factor, the ratio of peak to RMS. These terms help analysts quantify vibration severity and identify abnormal patterns. For example, a high crest factor may indicate transient impacts or bearing faults, while RMS is often used to assess overall machine health. Understanding these definitions ensures accurate interpretation of vibration data and supports effective troubleshooting. Definition and practical use: peak value analysis. The peak value represents the highest instantaneous amplitude of a vibration signal, typically measured in units such as mm/s or g. It is crucial for identifying sudden spikes or impacts that may indicate mechanical faults like looseness or gear tooth damage. Peak measurements are often used in alarm settings because they quickly reveal dangerous conditions. However, relying solely on peak can be misleading since it does not account for overall energy or sustained vibration levels. Analysts should interpret peak alongside RMS and crest factor for a comprehensive view. In practice, peak values are extracted from time-domain signals using sensors and data acquisition systems, and plotted to monitor trends over time. Significance and calculation: peak-to-peak measurement. Peak-to-peak value is the difference between the maximum positive and maximum negative amplitudes of a waveform. It represents the total excursion of the signal and is useful for understanding the full range of vibration displacement or acceleration. This metric is particularly relevant in systems where symmetrical oscillations occur, such as rotating machinery. A large peak-to-peak value may indicate severe imbalance or misalignment. Calculation involves identifying the highest and lowest points in the waveform and subtracting the latter from the former. While peak-to-peak provides a clear picture of signal extremes, it does not convey energy distribution, making it complementary to RMS analysis. Energy representation in vibration, RMS value and its importance. RMS or root mean square is a statistical measure that reflects the effective value of a vibration signal. It is calculated by squaring each instantaneous amplitude, averaging these squares, and taking the square root of the result. RMS is widely used because it correlates with the energy content of the vibration, making it a reliable indicator of overall machine health. Unlike peak or peak-to-peak, RMS accounts for sustained vibration levels rather than transient spikes. High RMS values often signal chronic issues such as imbalance or misalignment. RMS is also the basis for many industry standards and alarm thresholds, making it indispensable in predictive maintenance programs. Interpretation and diagnostic value: crest factor analysis. Crest factor is defined as the ratio of peak value to RMS value. It provides insight into the shape of the waveform and the presence of transient events. A high crest factor indicates that the signal has sharp peaks relative to its overall energy, which is common in cases of bearing defects or gear impacts. Conversely, a low crest factor suggests a smoother waveform dominated by steady-state vibration. Monitoring crest factor trends can help detect early-stage faults before they escalate. However, interpretation requires caution, as changes in crest factor may also result from variations in load or operating conditions. Combining crest factor with other metrics ensures accurate diagnostics. Parameter comparison and use cases. Each vibration parameter serves a distinct purpose in condition monitoring. Peak is ideal for detecting sudden impacts, peak-to-peak reveals total excursion, RMS measures overall energy, and crest factor highlights waveform characteristics. In practice, analysts use these metrics together to diagnose faults accurately. For example, a machine with high RMS and normal peak may have chronic imbalance, while high peak and crest factor suggest transient impacts. Applications span industries such as manufacturing, power generation, and transportation, where vibration analysis prevents failures and optimizes maintenance schedules. Understanding how to apply these parameters in real-world scenarios is key to effective predictive maintenance. Sensors and data acquisition, measurement techniques and tools. Accurate measurement of vibration parameters requires appropriate sensors and data acquisition systems. Common sensors include accelerometers, velocity transducers, and displacement probes, each suited for specific applications. Data acquisition systems capture time-domain signals and process them to compute peak, peak-to-peak, RMS, and crest factor. Advanced tools offer real-time monitoring and automated diagnostics, enabling proactive maintenance. Proper sensor placement and calibration are critical to ensure reliable data. Analysts must also consider environmental factors such as temperature and electromagnetic interference, which can affect readings. Leveraging modern technology enhances the accuracy and efficiency of vibration analysis. Avoiding misinterpretations. Misinterpretation of vibration parameters can lead to incorrect diagnoses and unnecessary maintenance actions. Common mistakes include relying solely on peak values, ignoring RMS trends, or misreading crest factor changes without considering operating conditions. Analysts should always evaluate multiple parameters and correlate findings with machine history and load variations. A case study example: a pump exhibited high crest factor, initially suggesting bearing defects. However, further analysis revealed intermittent cavitation events causing transient spikes. This underscores the importance of comprehensive analysis and contextual understanding in vibration diagnostics. Let's summarize key takeaways and best practices. Peak, peak-to-peak, RMS, and crest factor are fundamental parameters in vibration analysis, each offering unique insights into machine health. Peak detects extreme events, peak-to-peak measures total excursion, RMS reflects overall energy, and crest factor identifies waveform characteristics. Best practices include using these metrics collectively, applying proper measurement techniques, and interpreting results in context. By mastering these concepts, analysts can enhance predictive maintenance strategies, reduce downtime, and improve operational reliability. Continuous learning and leveraging advanced tools will further strengthen diagnostic capabilities in vibration analysis.